For this training video, we will discuss about the heat exchanger efficiency, wherein we will do a flow simulation using a counterflow heat exchanger, and we will observe the temperature and flow patterns inside of it. So using this flow simulation, we will be able to compute or simulate the heat exchanger efficiency, which is defined as follows: actual heat transfer over the maximum possible heat transfer. So we have to open the model. So on the previous training video, we have already discussed how to copy paste the model to your desktop. So as shown here, we will be using two fluids, which is the hot air and the cold water. Wherein the hot air is coming out at 600 Kelvin and moving at a 10 meters per second, while cold water is as about 0.02 kilograms per second at an initial temperature of 293.2 Kelvin. So they will be mixed inside this tube. So we will be using steel. So this is the Solidworks file for this one. So if we will see or look at the cross section, the model, we are able to see that the hot air will be flowing straight in this tube, while the cold water will be circulating outside of the straight tube and will be coming out from this outlet. So let's set up our model. So first we have to create our project wizard. So let's click the project wizard on the upper left. So we have to rename level 3 as stated in the manual, and we have to select the units as stated here. We have to select SI units, but using this manual, they use atmospheric pressure as their standard parameter on pressure and stress, so we have to change it already. Then click next. Then we will be using in the analysis type, which is internal, and we will be conducting heat conduction. So we have to check the heat conduction in solids. So select internal, then select heat conduction in solids. If we don't care about the fluids, we have to select on solids only, but in simulation we will be using heat conduction in solids and the fluids. After that, click next. So as stated, we have to select the two fluids, wherein the liquid is the main fluid or the default fluid, which is the water, and the secondary fluid is the hot air, which is under the gas. So stated here, we have to select liquid and the gas, which is water and air. Okay, so as step number 6, we have to select a default material for our simulation, which is we will select steel stainless 321 as our default material. So click next and let's go to the stainless steel 321. Select the default material. So as you can notice, we have different material here that we could use. Then next, since we are conducting heat transfer study, we will select heat transfer coefficient instead of adiabatic wall. So as stated here, we will use 5 watts per square meter Kelvin, and the default temperature is about 293.2 Kelvin as stated here. Then the roughness is 0 micrometers. Okay, then next, so we have to set up the initial conditions under the thermodynamic parameters. We have to input 2 atmosphere at 293.2 Kelvin. So select, we will be starting at 2 atmosphere and default temperature. Then once finished, select this tab. Okay, so as you can see, we already have the setup, the level 3. So moving on, we have to specify the symmetry condition. So since the tube is symmetrical, as you can see, so we will be using computational domain as 3D simulation, but we will pre-select the under the size and condition symmetry. So we'll be using symmetry to save memory since the model that we will be using is similar left and right if cut in the middle, but the result will be computed as a whole of the assembly. So symmetry, then with where would it start? So we have to specify the 0 max x max value. So you can see it's already cut in half, but we stated symmetry, so the results will be computed as a whole. So we're just doing it for to save time in computation of the simulation. Click select. Then next, we have to specify the fluid subdomain. So since we have selected liquid as our default fluid type and water as the default fluid type in the wizard, so we need to specify fluid air for the fluid region. So click flow simulation and insert fluid subdomain as stated here. Select flange 1 interface and we have to select gases, which is air. So as stated here, select fluid subdomain, then select other, under gases select air. So this is our fluid subdomain. So one thing that we are not doing is to make the model transparent, to make it visually good for us. But another technique is to make a cutout to instantly select the faces that we are setting up. So as we go along, flange 1 inner face is already selected. This is flange 1, right? Okay. Then I forgot to set up the velocity in Z direction and negative 10 meters per second. So I have to go back to fluid subdomain and input velocity and Z at negative 10 meters per second. So negative because it is opposite direction of this axis in terms of Z. So we have to put negative 10 in order to move to specify that it's moving in a different direction. Okay. Then under static or under thermodynamic parameters, we have to set up this at 1 atmosphere and 600 Kelvin. So I have to go back and set up the thermodynamic parameters to 1 atmosphere and at 600 Kelvin. So it's already hot. Then check. So we have already the fluid subdomain. Then we have to rename it to hot air just for uh, quick tracking. So you need to right click and rename it. Okay, we have the setup for the hot air. Then Right click on the boundary conditions. We have to set up the water. So we have to select phase 2 of water inlet lead 2 and select inlet mass flow and input the parameter to 0.01 kilograms per second. 0.01 because the symmetry plane is cut into half. So since we select 0.01 and it will be computed as 0.02 in our analysis. So we have to select boundary conditions, inlet mass flow, select the phase at a value of 0.01 kilograms per second at initial temperature of 293.2 Kelvin. Select. Okay. So we have to rename it inlet mass flow cold water. Then we have to select the water outlet lead. So the water outlet lead is pressure opening and is coming out of an environment. And the accepted environment pressure is about 200 to 650 Pascal. So insert boundary conditions, select environment pressure, select the phase lead 2. The thermodynamic parameters is 293 to, so 2 atmosphere is equivalent to 200 to 650 Pascal. And we have this setup. So we have to rename it at environment pressure warm water. After that, have to select the air inlet lead inner face in contact with the fluid. So inlet velocity normal to phase at 10 meters per second. So the inlet velocity is coming at 10 meters per second at temperature 600 Kelvin. So I have to correct this one. The thermodynamic parameters is at 600 Kelvin. Okay. Then if it's coming in, it should go out. So we have to set up the environment pressure to 101.325 Pascal and 600 Kelvin. So insert boundary conditions, select the lead outlet. So environment pressure going out at 1 atmosphere and the temperature is about 600 Kelvin. So we have to remain it environment pressure air. So I forgot to put air here. Definition. Alright, so we have the boundary condition setup. Okay, we have to specify the solid material. So we have to select the air inlet leads and the water inlet and outlet leads to insulators. So solid material, select this one, Lead 3 for predefined gases and minerals insulator. So there is no heat transfer through this insulator. So that's it. Then we have to specify the volume goal. So under the volume goal, you have to select tube and select the average temperature solid for the tube. Click OK. So right click on goals, insert volume goal, select tube, and under select tube, select for the temperature average solid. So we have to look for that one. Temperature of solid. So it's underneath. So okay. So select average temperature solid. So we have this VG temperature solid one. So we have to rename it to average T of tube. Then save it. So we already have the setup. So we need to run the solver. Run the calculation. Click run. So in this simulation is already running the solver. So we'll just wait to finish the iterations and the computations, and we will close the solver. Okay, once the solver is finished, we will close it, and let's look for the results. So first we have to view the goal. So what is the volume goal of average T of tube, which is 343 Kelvin. So let's check results. Goal plots, insert, and you have already the VGAVT of tube. So it's about 343.15 Kelvin. So it's almost similar to what the manual gathered. Okay, let's go to the cut plot. So using cut plot, we have to select plane 3 and select temperature as the selected parameter at 255 levels. So we have to adjust the maximum and velocity at 0.004 meters per second from between 0 and 0.004 meters per second. It has to display this kind of simulation. So let's do this. So let's make this one. So cut plot, insert. So why we select plane 3? Because it is the phase that is showing the direction that we need. Then contours. Then you have to select the temperature of fluid. So we have to check this one, adjust minimum maximum. So maximum velocity as the vector. Options. So let's go this one, vectors, velocity, and temperatures. Temperature of fluid. Then minimum maximum about 0.004 meters per second. Okay, then once you set up this one, contours is in temperature of, yeah, temperature only. Okay, so we have the setup. So as you can see the arrows, so this one is pointing out to this direction and to this direction. As you can see, the hot air is passing to 600 Kelvin, and this one is the hot water. Okay, so we have to adjust the parameter display range to 300 Kelvin to make it more of visually uh, visible for us. So select this one, change it from 600 to 300 Kelvin, and we will see the change in temperature of the cold water to a warm water. Then see we have this heat transfer already as the hair passes through this tube. Okay, now we will display the flow trajectory using inlet mass flow of cold water and select the velocity to 2.04 meters per second. Should be able to get this simulation. So let's hide this and 7. So pre-select the inlet mass flow, then use flow trajectory. So as you can see, we will select according to the manual. Appearance by velocity, use pipes. Velocity 0.004 meters per second. Guess the minimum maximum 0.004. Guess the levels 50. See, we have the pipe, so make it transparent and remove the cutter. So we have this flow trajectory, so we have to do animations. So as you can see, there's already the flow of the fluid of the water passing through this inlet. So for better visualization, change the angle of view. You can see the cold water is passing through this one. Then we could also add up another one. So pre-select the air, flow trajectory, insert, use pipes, to use bands and lines with arrows, use 50, select velocity, same. Okay, let's do the animation here. You can see the air is passing through the straight tube. While there's the cold water will be passing through this one. Right. So see the temperature distribution. We will select the temperature. Alright, so you can see we have the cold water and warmer water, while the fluid is consistently at 600 Kelvin. let's go to the surface parameter. So the select environment pressure. So we'll select phase of the water outlet lead. So we will be able to get the value of the temperature of fluid at 300 Kelvin. Okay, let's set up surface parameter. So let's hide first and go to the surface parameter. So before we go to this one, we will select the water outlet lead 2. So this one, and go to surface parameter insert. So as you can see, it has already selected the face at lead 2. So you have to select all and show. Okay, so under the surface parameter, we could see what value we need is temperature fluid Kelvin. So this one is about 300. No, the average is 299.76. So it's similar to the value that we will be getting here in the manual. So then we select the environment pressure at air. We should be able to get the value of 585 Kelvin. So let's go closer. Face leads. Remove this one. So pre-select inlet velocity, environment pressure, Kelvin, surface parameter. Okay, we'll just make another one. Select environment pressure air, insert, then show, select all, show. Can see we have the outlet temperature at 585.55. Alright, so with this one, with this value, we'll be able to compute for the heat exchanger efficiency at 600 minus 586.5 over 600 minus 293.2 Kelvin, which is the efficiency about 0.045. So you can see the flow simulation as a power tool for heat exchanger design. So you can see Solidworks can provide you the computation for the heat exchanger using this tutorial video. So show all and the cut plot. That's all for the heat exchanger tutorial. Thank you.